Swayam Prabha. Digital India. Educated India.
Welcome to today's lecture. This is continuation of design analysis of orbit motor part 3. Today we shall discuss about how to find out, how to formulate the output torque, stress, deformation and gap at contacts. Now, if we look into the figure, this is an inner view of orbit motor, where we have drawn a line through the contacts which are separating high pressure zone from low pressure zone, or in other words, the expansion mode to the compression modes. Now, what we have done, we have joined, we have considered a line here, and if we consider the width of the star or ring, then we may consider this is an beam where the pressure are uniformly distributed over this length joining two points. Then we can consider the total force acting at the middle of this beam, so equivalent force. Now, the torque must be equal to this equivalent force F I into the distance R I, which is from the instantaneous center of rotations. Now, here one may confuse that we are considering the torque about the star. Why we are considering such a distance? The reason is that what we have considered, this is the equivalent system we have considered. In that equivalent system, what we find that as if there is a fixed drum in which this drum is rotating. Here, of course, if we consider the drum, that is a friction drive which is not positive, but let us consider these are the two gears. So, definitely to calculate the torque, what we can find that as if this body is rotating about this pivot point by this force. So, definitely to rotate this body about this point, whatever the torque, that is in vector product R I into F I, this is R I into this is F I, this is half of the distance. So, that torque must be the output through this body, which is nothing but the star. So, we can write down this is the torque. Now, this is sometimes it is called energy method, but whatever may be the name, in this way we can find out the theoretical torque output of this machine. This is the distance R I, we should always remember. Now, I have drawn another figure here. In this figure, again I have shown here, apparently slightly it has rotated by this angle. In this case, as if it has not rotated it is at this 0th angle. If we remember our earlier axis system, so this is the x axis and this is the y axis, this is the reference axis which is coinciding with the ring gear. Now, here we must know, because we will refer ith chamber or roller etc. In this case, we have considered this is roller 1, roller 2, roller 3 etc., etc. Therefore, this must be the jth roller. In this case, as we see in this figure, we have considered 7 roller, and as well we find the lobes in the star are 6. Okay, number of lobes the star in 6. Now, also we consider the chamber 1 which is in between 1 and 2 roller, chamber 2 which is between 2 and 3 etc., etc. So, this chamber at the 0th position, that must be chamber 7 or zth chamber, which is in this case 7th chamber. Okay. Now, obviously, the instantaneous point of rotation of equivalent drum is now situated on the x axis. Now, this whole body or the star is revolving around this axis in the anti-clockwise directions, whereas this body itself rotating in the clockwise directions. So, output will be clockwise looking from this side. Okay. Now, in this case, we have considered the high pressure zone and low pressure zone separated by this line, and these two contacts we may consider active contacts. First of all, these two contacts are active contacts. All contacts which is joining the instantaneous center of rotations and the screw node, which is nothing but the center of the roller, then these are the active contacts, and among these active contacts there will be 7 active contacts. Among these active contacts, these two are, you can say, the critical contacts which are separating the chambers from high pressure zone to low pressure zone. Now, instead of considering the axis, the beam like this, we may also consider the all contacts points joined together, and we get, in that case we will get 7 such line, which obviously not equal in length. We may consider, however, that if we consider these are the critical joints which are separating high pressure zone to low pressure zone, we may consider in this side there will be the pressure, each chamber is having equal pressure, which is high pressure. Okay. Here of course, I have considered that apparently this is in neutral conditions. We do not know what is the pressure history. It can be shown that even if we consider this is in high pressure zone, or if we consider this is high pressure zone, the pressure the torque calculation will show the same value. Okay. Anyway, if we consider this is in high pressure, these 3 are high pressure. So, this is experiencing high pressure, and again on these lines pressure distribution will be uniform, equal pressure, but keep in mind while this is moving, these lengths are changing. So, these lengths may not be equal, are normally not equal, and on the other side this blue lines indicates these are separating the chambers, adjacent chambers by these contacts, and joining these lines we consider the pressure is the outlet pressure. One may consider this is 0 and this is the differential pressure. this will also give the same torque value, this would give the same torque value. Now, however, the equation for this will be different. In that case, what we are considering, say this is I is varying from 1 to Z, any chambers, in that case this is the length. So, force will be at the middle of that and then that multiplied by this distance. Say this is a typical one, is shown here, only one chamber I have shown the pressure is being distributed like this. Considering this equation will be better in a sense that actually in such machines we will find later that the gaps are generated here. So, case may be that pressure are not distributed over the whole length uniformly. It might be the pressure is non-uniform. In that case, if we can suppose this pressure distribution is non-uniform, then if we can consider such mapping, then we can accurately calculate the load and this distance, the distance from that load to this instantaneous center of rotation, and this will give us the more accurate torque. That is the purpose of considering the pressure distribution in that way. So, here I have written that due to the inner chamber leakage flow through the capillary passage formed by the lobes adjacent to the active contact, and at the flow distributor valve the pressure within the chamber may vary. Not only this, we should remember the flow distributor valve is very close to that. So, due to that there may have the pressure change due to leakage through that. So, once the leakage through that all the paths are considered, we may have different pressure history instead of the ideal pressure distribution. Now, let us, for the simplicity, let us consider there is no variation of this leakage. Then to find out the length, we must know these contact points which can be calculated from the geometry for a particular rotation, for a given rotation of the output shaft, and then we can find out that length and we may consider the pressure PCN, that is in that chamber the pressure is PCN and the length is LIN, and so this will be the force. We can calculate the force in this way. Now, we can see the variation here. Now, look at this variation. You can see these lengths are varying. Okay. Again we will see this. So, we have just shown one chamber operation rotation for one chamber. Again you can look this how these distance are being changed, and we have considered that this is the midpoint, which can be this is the midpoint. So, this geometrically this we can calculate and easily we can find out the forces. We can define this distance and lengths in the vector form and we can do the vector multiplication. Okay. So, in that way torque can be calculated. Okay. Now, what we have calculated so far, that is the ideal torque output of such machine. Now, in this machine, first of all, if we consider the assembly of rotor and stator, we may consider that this is just exactly fit. This means neither it is interference nor any gap at these contacts when these are assembled. In that case, we should consider that there is no interference speed, nothing is there. Now, due to the pressure we are considering now the pressure inside. Once there is a pressure means load and there will be deformations. These deformations means there will be may have gap, the contact points will be deformed. In that case we should consider the several losses. One is that at that contacts when this is moving on that, earlier we have examined that this is having both rolling as well as friction. So, sliding, rolling and sliding. So, if we consider the combined friction there, definitely there will be one pressure loss, and also this what the length we are considering ideally, that may also not exactly, because the contact has now deformed. So, length is changing, due to that there will be variations. Now, let us consider that there is some interference fit to reduce the gaps, etc. In that case, due to that interference fits, another additional torque will be required, which will not be available at the output shaft. Apart from that, there may have some error also. Considering this, one can carefully express the output torque in this form. Now, we will see that what are these parameters. Li is the ideal geometric length of a line joining two transition contact points at any instant, this one. And then Lia effective length of line joining two transition contact points at any instant. What is effective length and what is ideal length? Ideal length, what we are calculating initially from the contact points without considering any deformation at the contact points. Now, if we consider there is a deformations, then contact points may shift. If that can be calculated, then we will consider that this will be definitely the deviation of the ideal torque. So, that is there. Now, then what is MLH? It is called load holding resistive torque without fluid pressure. This can be calculated or experimentally can be founded out if there is some interference. Even if we consider the ideal fit, still there may have some frictional resistance to move this rotor. So, that is why we can find that initially to start that motor you need some pressure just to rotate without any load, that you may consider the load holding torque. That is that this means that we need a torque to start this motor without any load, that is load holding torque. On the other hand, this load holding torque is again we can name that is a starting torque required. Now, this obviously this increases depending on the fittings. If the fittings is too tight, in that case this part will increase, that can be estimated. Also, this is found out normally by from the experiment. Next, we consider the theoretical torque at starting pressure. That means, when what we will see that we are giving a pressure, but still this is not moving. So, that pressure into the when pressure is working on these machines without moving, that is the load holding part. But once it start moving, what will happen? Due to this forces present there will be a friction. So, considering this friction coefficient or the correction factor, we have given the name to account torque loss due to the starting pressure. So, there will be another loss. So, that this means that actual available torque is this much. the ideal torque, then there is a variation in this length. So, that part it will be slightly less than this actual torque, then this load holding torque, and then when it is starting there is a friction, due to that there is another loss. So, this is the total loss. Now, this we have considered that there is no deviation in the eccentricity, and if we consider further deviation in the eccentricity, there will be further loss. So, this amount this much amount can also be considered. So, this is a proposed model to estimate the available torque. Okay. But we may this measuring such this error or shift in center distance is very difficult. So, this we may neglect, or in other words, even if possible, if we can measure or we can estimate that, then whatever additional loss, that can be attributed to this one. Okay. Now, the instantaneous torque efficiency, now we can, this is the ideal torque and this is the output torque. So, this may be considered as a efficiency of such. Again, for force equilibrium, so this each chamber force and this efficiency must be equal to this ideal force at the contacts offered by, this is the resistive force, this is offered by the elastic deformation of the body. So, we can equilibrium in this way. Now, if we consider this is due to the ideal pressure, then this factor is 1, and then we will find this force is equal to the pressure force. Okay. But actually we will find that whatever force is there, this is more than the pressure force. Now, local deformation occurs at contacts initially due to interference fit, if any, and then due to fluid pressure. Therefore, it offers the normal force F n, which is expressed as follows: F n is equal to F h n and F p n. F h n and F p n are the reaction forces due to the contact deformations for interference fit, this is for interference fit, and then fluid pressure respectively. Say for example, there is no fluid pressure, let us consider. So, we do not need, or in other words, if we consider that there is no torque, output torque is required. So, at 0 pressure, ideally just flow is given, it should be able to rotate, but what we will find that it requires some amount of torque because there is a interference fit. So, this means that there is already some contacts are deformed, and due to that the force H n is there. Now, what we do, we add fluid pressure because the output torque is there. So, therefore, we should consider at each contacts there are two forces acting, originally due to the interference and then due to the pressure. If there is no interference, we can consider this part is 0 and normal force equal to due to the force due to the pressure. Now, with ideal size of rotor stator, gaps occur at few contacts which separate chambers in expansion mode, that is chambers with high pressure, and even at active contact separating low pressure chamber from high pressure chamber. Now, here I would like to mention that we are trying to find out the forces in each and every contact. Then we have considered that apparently this one, we may consider that this line which is separating high pressure to low pressures, then this is a beam. Now, this beam is supported by how many supports are there? At least this will be the number of chambers divided by 2. number of chambers plus 1 divided by 2, either this or minus 1 divided by 2, it has to be. This is for the odd number of chambers, we are considering odd number of chambers. So, by that way, say for example, in case of this 7 chamber machines, this will be either 3 or 4. Now, in a beam there are 4 supports or 3 supports. So, this will be statically indeterminate problem. Okay. Now, also if you look into this the support and their direction of force, to find out the direction of force, what we can do, or we can join the instantaneous center of rotation to the center of the roller or center of the nodes of the envelope. So, we are getting the direction of the force, direction of the support. But if you look into the direction of the support, these are not parallel or not perpendicular to the beam what we have considered. This is at an angle. So, the problem to find out this the loads is not an easy task. We have to consider all the directions. Now, again looking into the direction of the force, we may find that in some supports are not taking the load at all, and as well we will also see that a gap is generated. Now, this gap, say this is the high pressure side. So, definitely beam supports are in the low pressure sides, and these two are critical, and we may find at some instances there a gap is generated. Once the gap is generated, you will find there will be the leakage. So, estimating such leakage is essential to improve the performance of such motor. Also, what we the valve is very adjacent to this. So, there also the possibility of side leakage like this. Here one is leakage through these contacts, another is the side leakage from this valve ports. Considering all such things, we can have a redistributed pressure, particularly where this capillary passage is there. We can have a distributed pressure over this chamber, and that distributed pressure, if you put on that, we will find a different force. Okay. However, depending on the pre-deformation due to the interference speed of star and ring, the gap may not occur at all for a reasonably high operating pressures. What we can do, we can make this as an interference speed. This is basically, such machines are called form closed. That means, even if without any force, there will be all contacts, all 7 contacts in this case, without any force, and geometrically that for contacts will be maintained. Now, if we put the interference feet means actually at some point we will describe that these rollers are oversized as well as the star are oversized. So, in that case what will happen, each and every contact, so assembly is difficult, but that is done with some technique, heating one element and cooling the other element, that assembly is possible. But once it is assembled, then there is whatever may be the small deformations will be there. Now, with the increase in pressure, that deformation will gradually decrease, and at one point with the higher pressure definitely there will be gap. But we can design such machines that up to the working pressure there will be no gap at the contacts. Only disadvantage of such machines will be there. At starting you need a starting torque, higher starting torque, but once it reaches at its working zone, you are not required, no leakage is there, efficiency will be higher, although some initial torque were required, but you may find that overall efficiency is more, or overall performance at least better than the ordinary I mean without interference fit machines. As the material of star and ring are usually steel, it may be assumed that they have same Poisson ratio and modulus of elasticity, and then we can consider the deformation at a contact is del n. This is along the normal directions. That means, in these directions this will be the deformation. So, this expression will give us this deformation if the force are known. Here we do not know how much is the deformation, how much is the force. We are trying to find out the force at each and every contacts. Okay. Now, A n is the bandwidth, half bandwidth, which is given by this formula. This is from Hertzian contact stress theory. So, you can this is perhaps known to you. We have only written in this form. Here this is the contact radius of the star and this is the contact radius of the ring. But you should remember, this plus sign means both are concave. Now, if one of that, but if you look into the star, this is having convex as well as concave. When this is a concave, then there will be a minus sign, okay, minus plus sign. So, you have to take care of that part. Okay. Now, what is this one? H A. H A is a depth up to which this deformation occurs. This is a complex things, but this we have to assume for such machines what might be this depth. H is average compliance depths. In this case, we have considered this depth is up to the center of the roller. So, this is equal to R m maximum, but this is an arbitrary. However, if we consider this is half of that or double of that, you will find this overall contribution to this will be negligibly small. So, it is a reasonably good to assume this H A is equal to R m. So, in all calculations we consider this is equal to R m. This radius already I have explained to you, radius of curvature. Now, for the dimensionless analysis, this formula is further simplified, which is given by this developed by Cornell, and this can be written in this form. So, this I have given this article as a reference. One can read to how this was derived. Once we reach here, then we can non-dimensionalize. It is like that. Now, earlier when we are non-dimensionalizing a dimension, we are simply dividing that one by the radius of the base circle or the describing circle of the ring gear, that is R 0. We are considering this radius R 0 of the biggest circle. Here it is a green circle. Whereas, when we are trying to non-dimensioning this force, what we do? We consider this force, normal force divided by B, that means this is coming per width, and then divided by del P I, which is coming as a per unit pressure, and then R 0 is this radius of the biggest circle. This, look into this unit, this is area and this is pressure. So, this must be also force. So, this becomes a non-dimensionalized. That means, once we calculate these deformations or force for a machines, considering this approach, then for actual pressure and actual width we can find out what will be the actual deformation or actual force. And beauty of using such non-dimensional analysis is that you can analyze the machines for a particular geometry, and then you can design, you can consider the pressure, actual width, flow rate, everything later to give the physical size of these machines, keeping the geometric relation same. Now, this is the deformations in the same way we can express in the non-dimensional form. Okay. Now, the contact deformation on star at the active contacts nth lobe of ring can be expressed. This is actually this is in the vector form. So, we can know not in the vector form, we would say that this is what we are doing, the actual deformations, total deformation. From there we are trying to find out what is the deformation in the normal directions. We have considered any deformations at any directions, then by this multiplication we are finding out what is the magnitude of deformation along the normal line. So, for that we need these operations. And then also this actual area of the contact can be find out, because we have calculated the half bandwidth. So, total bandwidth will be this much, and B is the width of this star or ring. So, this we get actual area. Okay. Now, then finally, we can express this formula, the F n non-dimensional is equal to 0.44 into delta n. Look at this, this is not for the both star and ring material as a steel, we have considered that. So, Poisson ratio is around 0.3, with that we get these relations. Okay. This is very simple relations. Any force in the normal direction is equal to 0.44 times of the deformations. So, this analysis become easy. If the calculation of contact deformation, forces etc. caused due to the interference fit or oversized star and ring, it is assumed that excess size is deformed in the direction of the normal to active contacts, that is in the direction of line joining the instantaneous center of rotation to the center of lobe or roller in ring. Now, here I would like to mention, you see, if you consider a simple cylinder and a whole and cylindrical body perfectly round and they are in interference fit, you may consider deformations over the contraction of the cylinder is uniform over the periphery, expansion of the cylinder is also deformed uniformly over the periphery. In this case, we had to depend, I mean such interference is taken care by few contacts only. So, most likely it is not uniformly distributed. Okay. And if you think, if you try to visualize, there is a possibility of that unstable conditions. That means, for such a interference fit, such interference fit, ultimately you will find this star will try to take a stable position. What is that stable position? You will find one of the chamber will be either in the outer dead center or bottom dead center. Here you can say this is at the outer dead center. So, this is one stable conditions. Next, Next stable condition will be this one of these two chamber will be inner dead center. Okay. So, which is precisely can be found out by the pi divided by z into z minus 1. So, every after that angle this will be in the stable conditions, or in other words you will find this machine, if you leave this machine it will try to go to that position for its stability. Now, in other conditions, suppose if you hold that shaft at the other conditions, what will be the situation in the machines? This machine, due to the pressure, it is giving a torque. You will find apart from that there is some unbalanced amount within these machines. That means, to hold the shaft at that particular position you need some unbalanced torque, although the magnitude is may not be very high, but this unbalanced torque is there. So, in the force analysis definitely such contact forces giving this unbalanced torque. So, while you are calculating, automatically this should also be taken care of. So, here I have shown that the equation using equation 9 and 10 one can try to find out the forces, but this we have to follow a particular technique that how we can find out these forces. Let F H n be the reaction force due to the contact deformations for interference at nth lobe, then we can have that summation of all such forces due to the interference at no pressure must be equal to 0. So, we must satisfy that condition to find out this force, and then we can consider this load holding torque must be equal to that force into the coefficient of friction into this R n. In that case, to calculate this R n, we have to consider this contact point to this distance, because here this is the normal force. So, this force is in this transverse directions, and that multiplied into R n will give the load holding torque. Mu c is the coefficient of combined rolling and sliding friction at contacts. This means that to rotate the shaft even there is no fluid pressure, the required torque is MLH. Speculatively, for such geometric form closed machine, this summation of forces may not become 0 in all the angular position of shaft rotation, and the rotor is virtually floating. As the rotor is virtually floating, the summation will become minimum. Floating rotor will assume a comfortable position by deviating from its ideal geometric positions, which I have explained. It will actually will try to take a position for which one of the chamber is either at the top dead center or the inner dead center or outer dead center or the inner dead. One is outer, one is inner, one is a top dead center, one is bottom dead center, whatever name you can give it to this. It is better to give this is outer dead center and this is inner dead center. Okay. We have also verified this in numerically, and that can be shown. Now, in calculating these forces Fpn part, that is the force due to pressure, first of all an arbitrary small deflection delta dn is considered in the dimensional numerical computations. We consider any arbitrary value small deformation in opposite directions of the resultant applied force. That means, suppose this is the direction of the force, we have considered these 2 points. Say shaft has rotated by a small angle for which these two are the critical contact points. So, we know these lines, we know this direction, we consider the transverse directions of this. Okay. Then we consider deformations are taking place in these directions. That means, whatever deformation is there, deformation is taking in these directions, which is perpendicular to this. First we consider. Let us give a very small, because this is dimensionless quantity, let us take 0.01.